So in this video, we are going to learn about the second traversal technique, that is the DFS traversal in a graph. Now, in the previous video, you did learn about something which was BFS, breadth first search, which was based on level. Now we will be learning as DFS, which is depth first search. Now this will be based on depth, depth. Yes. So why did I emphasize so much on depth? You'll understand. Again, similarly, you'll be given a graph and you'll be given a starting node. Assume the starting node to be 1 over here. Okay. The starting node is 1. This is 1. Okay. Now, you go to any one of the neighboring nodes. 2, 3, 4. Anyone you can go. So, for example, I decide I will go from 1 to the left neighboring node, which is 2. So, if you go to 2, you don't stop there. Very important. You started from here, you go here. And then you don't stop. You go depth. So you go to depth, which is 5. Again, you can either go to here or here. That is your choice. But generally, we go to the guy who is right at the first of the adjacency list, or from left to right. So 5 will be there. So you basically go like this. So it's like 1, 2, 5. Done. Now you've gone like 1, 2, 5. There is no further depth in it. So what you do is you come back and now you go to here, which is the 6. So you go to 6. Right? Now you went like 1, 2, 5. You came back. You went to 6. Now there is no depth of 6. So you come back. Now there is no further children of 2. So you go back. Now once this portion depth is completed, now it starts going to the next portion, which is 3. So you go to 3. Done. Now when you've gone to 3, now again, either you can go this way or you can go this way. That is your choice. So I decide I'll go this way. So I'll go like 7. Okay. So I go 7. Now you're like 1, 3, 7. Now 7's depth is 8. Does not needs to be in down neighbor. 7's depth is 8. So you go to 8. 8's depth is 4. So you go to 4. So apparently, you started from 1, you came to 3, you went to 7, you went to 8, you went to 4, and after that, you can't go because this is already done. So you go back, there is no further, go back, no further, go back, no further, go back. So apparently this portion is done. Had there been someone else, something like 3, 4, 9, 10, then coming back, you'd have gone to 9, 10. So you go to depth. You go to depth at first. I hope that makes sense. So this will be the DFS. Again, it's not necessary that you go like this, then this. You could have done the other way, like 1, 3. Then you could have gone like this, 4, 8, 7. Then you could have gone to 2, then to 6, then to 5. You could have done that way. That is, as long as you're traversing in depth, any traversal type will work, but it should be depth. Okay, so let's change the starting node in order to understand the DFS traversal more. Okay, so assume I change the starting node to be somewhere around 3. Now assume this is the starting. So again, this will be the first point for sure. This will be the first point. Now from 3, you can either go here, you can either go here, you can either go here. Your choice. So I decide I'll go to 4. From 3, I decide I'll go to 4. So it'll be like 4. Then you'll go to 8. Then you'll go to 7. So it'll be like 3, 4, 8, 7. So 3, 4, 8, 7. So 3 went to 4. 4 went to 8. 8 went to 7. Cannot go further. Comes back. So this portion depth is completed. Now go the other way, which is 1. So you go to 1. You go to 2. Again do the same thing. 5 and then 6, or the opposite. It's like 1, 2, 5, 6. Now come back again. Now 3, will it go to 7? No, because 7 has already been covered. So if you start from 3 and you go in this, then you go in this, this will be the DFS. There can be plenty of DFS depending on the starting node. Yes, depending on the starting node. And which algorithm, if I ask you, which algorithm usually goes to the depth, solves it, comes back? Yes, you said that correctly, recursion. That is absolutely correct. The algorithm that always goes in depth, like if you remember, this kind of algorithm is, do you remember? This kind of algorithm is nothing but recursion. And if you have not seen the recursion playlist, I will highly recommend you go back and watch my recursion playlist at least till video 7, at least from video 1 to video 7, because entire graph without recursion will be nightmare. You need to understand how graph works in DFS Traversal, otherwise it will be a big mess. So again, for this graph, where do you store that? You store this graph in an adjacency list. That is something which you will do. So please go and store this graph in an adjacency list. So this is how the adjacency list for this particular graph will look like. Now, assuming the starting node is given as 1. Okay, assume the starting node is 1. What will be the initial configuration? Again, similar to BFS Traversal, you will first create a BFS. So first create a visited array. Again, please go and check if it is a 1 based indexing. So if you see a 1 based 1 to 8, so please create like a 9 size array, 0, 1, 2, 3, 4, 5, 6, 7, 8. So a visited array is what initially you will start off with, and whatever is the starting node, just mark it as visited and everything else will be staying as 0, similar to what we did in BFS. Done. What will be the next step? Remember this. The next step is going to be whatever is your starting node, you call a recursive function. Remember this. You call a recursive DFS function from that. Okay. Now what you will do is this DFS of 1, I'll write the code somewhere. DFS of node, what this will do is the moment it gets into the function, it states, hey dude, listen, this guy is done and this is a part of my DFS. Well, you can just add a list and you can say this is a part of my DFS. Okay, so this is the line where you will do the DFS traversal because you're visiting a node, so stored. Now what you do is, remember this, what you do is you went to 1. Now either you can go to 2, either you can go to 3. You go this depth or you go this depth. So you travel the neighbors. Either you travel 2 first or 3 first, that is your headache. But you travel the neighbors at first. So how do you travel the neighbors of 1? Very simple. They're stored in the adjacency list. If you carefully see, they're stored in the adjacency list. So for any node, you go to their adjacency list. You go to their adjacency list, right? So this is nothing but adjacency of 1. So this is the vector. This is the list. So that is what you'll pick up. That is what you'll pick up. So pick up the list and run a for each loop in it. So these are the neighbors. Run a for each loop in it. Adjacency of node. So this is the list of neighbors and you're running it. And now you go depth by each node. So first you go to the depth of 2, then you go to the depth of 3. So first go to the depth of 1 IT, which is 1 neighbor, and in the next iteration, the next IT will go. So imagine this to have 2, 3. What will happen? First a call of 2 will be made. So it will be like DFS of 2 is made. Then when this completes, the call completes because it is a recursive call. It's a recursive call. When it completes, then it goes to DFS of 3. You need to understand this. Okay. So it's basically something like, okay, let's get back. It's something like, okay, first we have 2. So let's call the DFS for 2. It will go and it'll complete, like go to the depth, and then come back. Then the next guy will be 3. Then it will go to DFS of 3 and then come back. So it's like DFS of 2 will be performed in depth, then DFS of 3. But you don't visit every time all the nodes, because when you go to 2, it will have the neighboring as 1, 5, 6. But from 2, you will not go back to 1. From 2, you will not go back to 1. So it's very important. A node which has been visited in its traversal, you don't visit it again. So what you do is, you say, okay, listen, this node has to be unvisited for me to go into the depth of it. This node has to be unvisited for me to go into the depth of it. Simple. So this will be the simple lines of code that you need to execute. So what will happen is, DFS of 1 will come and will mark it as visited. Now it has two neighbors, 2 and 3. So it will go to the depth of them, right? So for 2, it again goes and checks there is 1, but that is already visited. Then there is 5 and then there is 6. So it will go for both DFS for 5 and then DFS for 6. So how is the call coming up? First the call was for 1, right? So you can write 1. Next the call went to 2, right? Next the call went for 5. So now for 5, when you go to 5, remember this by the way, when you go to 2, you'll mark it as 1. Now you go to 5, mark it as 1. Now for 5, what happens is, see here, for 5, the neighbor is 2, which is already marked. There will be no further calls. So 5 will say there are no further calls. There are no neighbors. So I don't call anyone. So I will come back. I came back, right? Now DFS of 2 goes to DFS of 6. 6 says, do I have neighbors? I do 2, which is already visited. No further calls. Comes back. Now 2 says, do I have any other neighbors apart from 5 and 6? No. I go back. 1. So 2 is completed. So initially when you started with 2, it is completed. Now the next guy 3 will be occurring. Next guy 3 will be occurring. So you go to 3 now. 3 is marked as visited and now you're traversing 3. So the next we go to DFS of 3. So let's check out who are the neighbors of 3. So the neighbor of 3 appears to be 4 and 7. So first we will go to 4, then we'll go to 7. But apparently what will happen is, when you go to 4, 4 in turn will go to 8, 8 will go in turn to 7. So 4, when it goes to depth, it will visit 7. So thereby this call was made. Depending on where 4 lies on the adjacency list, we made this call. If there was something like 7, 4, you would have gone like this. So it depends on the adjacency list, which format, like which traversal you will traverse. Okay, so for 3, who are the neighbors? 1, no. 4 and 7. 4 and 7. First we go to 4. Perfect. Let's go to 4. Then we will think, shall we go to 7 or not? Then we will think, shall we go to 7 or not? We are not sure as of now. But DFS of 4 is sure. Let's go to 4. Market is visited and 4 is there. Perfect. Now let's go to 4. Who are 4's neighbor? There should be 3 and 8. 3 is already visited, but 8 is not. So let's go to 8. Very simple. Again, if you're going to 8, market is visited. At the moment you go to 8, who are 8's neighbors? 4. No need to go. 7. Okay, interesting. Let's go to 7. And 7 is visited. Now, who are 7's neighbor? 3 and 8. Those guys are already visited. You have already traversed them. So you do not go. You do not go. Yes, you do not go. So apparently 7 is done. 7 says, I don't have anything. My recursion is done. Can you just go back? He's like, okay, let's go back. 8 says, I don't have any neighbors. Can you please go back? He says, okay. 4 says, I don't have any neighbors. Can you please go back? Yes. So this 3 went into one of its neighbor 4. Will it go to the next neighbor 7? No, because 7 was visited by this path. So there is no need to again go and visit 7. So this supposed neighbor is no more visited. Thereby, the DFS is this portion. This is your DFS call. So if you carefully observed from here, whether you went like this or whether you went like this, was dependent on the adjacency list. So I hope you've understood the technique. Now it's time to check out the code. So as usual in the code, so the C++ code is what I'll be typing, and on the left you can see the entire Java code in the similar format. So you can just follow the Java code and you can understand every line while I type the C++ code. The syntax is almost identical. So what do we have? We have the number of nodes and the adjacency list. You don't need to create the graph because that is always given to you. So if you carefully observe, it's a connected undirected graph and it says the starting index is 0th vertex. So something to observe, it's a 0 based indexing graph. So this will do, right? Perfect. So starting index is 0. So you can say the start is 0. and you need to store so you can create a list in order to store the DFS ls. Okay, so over here you can go back and say cool private, and right here what you can write is void DFS. This will be the node, correct? You need this particular adjacency list, so please carry the adjacency list as well. And what is the next thing that you need? You need the visited, so please carry the visited, and you need the list which stores the particular DFS, so please carry the list as well. Now what will you do when you enter? So the moment you enter, you remember this is mandatory, and you add it in the node into the vector or the list. What's the next step? The next step that you do is you traverse for all its neighbors. So this is how you traverse for all its neighbors. Remember this is the way in which you traverse all its neighbors. Okay, so now what is the first thing that you do? If this neighbor is non-visited, very important, if this neighbor is non-visited, you call DFS IT adjacency visit and just pass on the parameters, and this is how the DFS will be. And over here what you do is you call the DFS the starting node. The starting node can be anything. Pass on the adjacency, pass on the visited, pass on the ls. Once the entire DFS has been completed, you return the ls, and now you can just go and compile. Hopefully it runs. So if you see visited of n, okay, as usual, our common mistake, this will be v. If you see the output is correct, let's quickly submit this. So internally the code has also been written in such a way that it follows the adjacency list, so you don't need to worry, the code will be working fine. So this is what is the DFS traversal of a graph. So let's talk about the space complexity. So what will be the space complexity? How many nodes are we visiting? At max we are visiting n nodes in our traversal, so we can say that we are storing n nodes in those DFS traversal. We are using bgo of n for visited, and the recursion stack space at the worst case, because what is stack space? If you remember recursion, this is the stack space. So the worst case, if I give you a graph like a skewed graph, you will end up going like 1 2 3 4. So the recursion stack space at the worst case can be bgo of n. So I can call it near about bgo of n if we do not include the adjacency list. What about the DFS traversal? So how's the DFS traversal? It's a function, and then it iterates on the neighbors, right? Iterates on the neighbors, and for every neighbor it calls the function. This is how it is, right? So this function will always be called for a single node. This function will always be called for a single node, right? And for any node it will just be called once, because you traverse a node single time. For node 1 it will come once, for node 2 it will come once, and for every node we will have a certain number of neighbors that it is iterating. So can I say for an undirected graph, these neighbors, for 3 the neighbors are 1 7 and 4, which is the degree of the graph. Can I say it is the degree of the graph? Degree of 3. Yes. And for every node, can I say it will be the summation of degrees? So can I say it will be the summation of neighbors or the summation of degrees? I can say summation of degrees, because for every node it will be the number of neighbors plus number of neighbors plus number of neighbors, which is equivalent to degree of a node plus degree of a node plus degree of a node, which is equivalent to summation of degree, right? So what is the summation of degree? If you remember the first lecture, that is 2 into number of edges, and then for every node you're calling the function once, so bgo of n for calling the recursion once. So this is the time complexity for an undirected graph. For a directed graph, it will depend on the number of edges, so this 2 will go off, and the number of edges is what it will boil down to. So guys, I hope you have understood the entire explanation as well as the code and the time complexity and the space complexity. Just in case you did, please hit that like button, and if you're new to our channel, what are you waiting for? Hit that subscribe button right away. With this, I'll be wrapping up this video, and yeah, for the DP series and the SD sheet, You can find the link in the description. Make sure you check it out. And let's wrap up this video. Let's meet in some other video. Till then, bye bye. Take care.